Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My great pleasure to have Nick Weaver from Berkeley ICSI Research Institute, Nick's institute, and as well as UCSD Research Group have been working together uncovering the underground economy, as well as a bunch of other network security, which has made really significant impact. So I'm really happy that Nick is here with us and telling us about two pieces of work. So there are two talks. The first talk is about Netalyzr, and he has some very exciting story on some ISPs. I will not, you will hear all the exciting story from Nick firsthand. The next talk is about the spam underground economy. Okay, thank you, Nick.
Thank you very much. The way I figured it, if I'm flying up to Microsoft, I might as well give two talks rather than one. Also, it gave me an excuse to prepare the second talk. This first one I've given in a couple of places because Netalyzr is this big network measurement tool that we've built at ICSI. It has been widely successful at this point as network measurement tools go. How many people have run it before? Well, if you haven't, you probably want to run it on your own network just to find out what exactly is broken. If you have, run it again, because we keep adding new tests. Also, it's really fun to run on random hotspots. So this is joint work with Christian, Boris, Gregor, and Vern. Boris, while he was at ICSI as a visitor. And this work is sponsored by the National Science Foundation with additional support from Google and Comcast, as well as EC2 Time from Amazon. And again, opinions are myself, not of those of the sponsor or co-authors. So let's start off with an anecdote of how web search is supposed to work for people. Well, they type in something into the browser's search bar. In this case, it's Internet Explorer 8. And the browser goes, OK, ask the DNS resolver, what's the address of the search engine, which by default is Bing. I'm using this example not because I'm at Microsoft, but because this is what actually happens for more people. The result comes back. The request goes to the web server. And the reply goes. However, we saw something interesting for about 1% to 2% of Netalyzr sessions. So not a huge number, but enough to be really significant. And I will get back to what this was later. But as a teaser, the ISP had installed some sort of DNS appliance in their network. And some third party, for this purpose is unknown, was running a proxy server. Again, the user does a query. The DNS resolver returns the address of the local Akamai node that's serving Bing. And the resolver appliance in between, or the appliance in between the resolver and the user goes, oh, wait, this is a request for Bing. I'm going to change it to the address of a proxy server. The request goes to the proxy server. And in this example, nothing happens. Request gets forwarded to Bing. Results come back. And, well, nothing happens. The proxy forwards it on. And the user has no understanding of what happened. This is just one example of how the network really works in practice for people. And it gets on to this lovely theoretical view of the internet we have, where we've got our server over on that side and the user on this side. And traffic goes back and forth. But in reality, the path our packets take might as well be Napoleon's March on Moscow. We have fragments are just not allowed by the network these days. We have hidden proxies on various networks for DNS, HTTP, and other protocols. We have this problem called buffer bloat, where the network can do great file transfers, or the network can do interactive tasks. But if you try to do both at the same time, you're in a world of pain. We have this problem of NX domain wildcarding. Anybody who thinks that an error should be properly reported back to the computer doing it is unfortunately disagreeing with most of the ISPs out there. And we have this where ISPs were man-in-the-middling search sites for up until a month ago, completely unknown reasons. And finally, this lovely gentleman created the home gateway. The home gateway, or NAT, is an abomination unto God and man. No fragments, broken DNS resolvers, FTP proxies, SIP proxies. If a NAT can break the network in a new and interesting way, there's at least one vendor whose NAT breaks the network in that particular interesting way. I think the way to put it, all NATs are broken differently. So we wanted a tool to know what the network actually is. So we wanted two rules: an easy-to-use network survey for anybody. Basically, the motto is, so easy my mother can run it. And indeed, it is actually easy enough that I can have my mother run this tool.
Your mother installed the applet, Java applet, and all that.
She doesn't have to install the applet. It's 2 mouse clicks for the typical user. She's running a Mac. Windows XP has Java installed. Windows, by default, Windows XP is still your biggest market share. So for all those users, it's 2 mouse clicks. As well as a detailed diagnostic tool for expert, including what we colloquially call mom mode debugging. Tell your mother to run Netalyzr, have her send you the results, and now you know all the different ways her network is broken. And so we targeted the web browser with just 2 mouse clicks. And we did it in Java rather than JavaScript, because JavaScript doesn't allow us to do raw traffic. And we didn't do it in Flash, because Flash gives us headaches. But there's a lot of sneakiness in our tests. And
Flash give you headaches?
I've just looked at it, and their same origin policy is weird. One of the nice things about Java is it has blame the user bypass of same origin. So our architecture is rather distributed. We built a cloud-based service. So our front-end web server, DNS server, is running at IXE. All our servers are custom. We wrote them ourselves because they fold, spindle, and mutilate protocols in interesting ways. Then the test runs on a EC2 node. We right now tend to run 5 EC2 nodes at a time, but we've run as many as 20 when we're expecting a flash crowd. And this probes the network for everything. And then a result page is delivered. And then we fetch the result back. And now I try to do the bold thing of a live demo on the network. So let's get on the guest network. This doesn't count in the mouse clicks, OK?
While that's happening, let me ask you. So a couple of weeks ago, I was at a hotspot, and I would try to do a search in the browser, just as you described, Nick. And instead of actually getting some hidden proxy, what actually happened was instead of getting a big result, I got a result from some other search engine.
Oh.
It would hijack me away from Bing to another search engine.
That's interesting. We've contemplating adding in a test for that direct to our server, because if it's done using DNS, Netalyzr would capture it. If it's done using direct injection, we don't currently capture it. But we do capture direct 404 rewriting, which a couple of ISPs are doing, where the ISP looks at the 404 page and rewrites it. So this is the basic user experience. They see our web page. It's got a big start analysis button, although if we ask my sister who's doing marketing stuff, it's not big enough. They click the start analysis button. It gets redirected to a random backend node. And there's a Java signed applet dialog. That's mouse click number 2. If they click deny, most tests still run, just not all of them. And then it starts running, and the results display after way too much. And the guest network here is relatively clean. There's a little bit of port filtering, namely the Windows ports. Yes, even Microsoft is unwilling to allow the Windows ports onto the internet. And DNS passes through a firewall that's protocol aware. And there are a couple of minor bugs in the DNS server. Basically, it's not doing failover for TCP write. common, annoying, doesn't really matter until you want to start doing DNSSEC, and then when you start doing DNSSEC, this may be a problem. So back to the talk. Yes, it works well enough that I'm willing to do live demos in all my talks. So to give you an idea of the test suite, this is actually most of the test suite. We've added in 404 rewriting detection. We've added in some more DNS probing. We've added in UPnP queries. And it really depends what the PC is, how they react to the paper. The IMC paper committee loved our paper. The SIGCOMM paper committee said this reads like a data dump. One thing we have is lots of biases. Netalyzr is run by geeks. Far more Linux, far more Firefox than you'd ever expect in the real world. Far more OpenDNS than you'd expect in the real world. We have a tendency towards flash crowds. So our initial flash crowd was biased towards Comcast users. We recently received 20,000 visitors from Germany because we did a German, or Heise provided a German translation and a link to on their page. And as a result, a lot of German geeks go, oh, this is a really cool tool. We've participated in at least 2 IPv6 deployment tests. Tor Anderson's trial. If users had problems, it threw up Netalyzr. Comcast IPv6 deployment trial. And one online game has decided through no knowledge of our own that Netalyzr is a cool debugging tool. And this is a quote from their FAQ. None of this also worked. My internet is pwned. And the answer is run Netalyzr, post the results in the forum, and somebody who's a geek in the forum will actually be able to find out what's going wrong. We didn't intend this, but it shows just how usable this is for mom-level debugging. So one thing we do is we really exploit Java's same origin policy. If the signature is rejected, we are confined to same origin, and we wanted as many tests to run as possible within that. Fortunately, Java's same origin is actually amazingly permissive from our point of view. We can contact our own origin server on any port using raw TCP and UDP, as well as HTTP through the Java API. No objections. It allows us to do whatever we want. And since we have raw TCP and UDP, we can do anything that's network layer and above. We can play games with protocols. We can do direct DNS, all sorts. We can perform any DNS lookup. But the Java VM enforces same origin at DNS, sort of. If the answer is the origin server's IP address, that answer is returned. Otherwise, it raises a security exception of this request would violate same origin. You aren't supposed to know about any other IP addresses. But this allows us Boolean property tests on the DNS infrastructure. You do a query. It either returns the server's IP address or an error. So as long as it's something that's a Boolean property with the resolver itself, we can test it without violating same origin. However, if the signature is accepted, Java's sandboxing is gone. Java believes in a blame the user sandbox. There's one click to bypass the sandbox, and if the applet does something wrong.
What are some examples of the Boolean tests?
So for example, how is glue policy handled? Does the DNS resolver accept arbitrary in-bailiwick glue records? Does it accept in-bailiwick glue records only when they're in the NSRR set? Does the resolver validate DNSSEC is one that we will be able to do? Can the resolver fetch large responses over TCP? So for that one, we send truncate back with false. If it caches that, oh, it doesn't. And then when it retries with TCP, we send the true value. So this allows a large number of tests to be done.
Who accepts the signature of your Java?
Almost everybody.
The user.
The user.
So that's another click?
Yeah, that's click 2.
Is that the allow and deny click?
Yes. And I hate to admit it, but there's basically UI bugs involved that we are inadvertently but happily exploiting. The Java dialog actually is fairly reasonable for the Mac. It's not great, but it says the applet is requesting access to your computer. Deny, allow. Deny means run within same origin. We can't touch the disk. We can't touch the computer. So it could be much clearer, but it's OK. It's great for our purposes. It's kind of OK from a user education standpoint. Sun's dialog box, however, for Windows, what does this mean? This application's digital signature cannot be verified. It can't be verified because I'm running on debug. So I'm running with a non-verified self-signed certificate in this case. This is its dialog if it has no clue where the code's coming from. Run or cancel. Do you know what cancel means? Run with same origin. Run means run bypassing same origin. This is a textbook example of how not to design a dialog box to educate users. But it's great for us because it means everybody bypasses same origin. So the first result of interest is fragments and path MTU discovery. We test fragments by sending a 2,000 byte UDP datagram, so it should be just fragmented by the network. It's set. The ones sent from our server are set without df set, so things should refragment, etc. 8% can't send fragments, 8% can't receive fragments. So basically, fragmentation to the client does not work on the modern internet. This is due to stateless firewalls and NATs. It's easy to make a stateless firewall break all fragments. People do it all the time. Those who can send fragments may have an MTU hole. 3% of the sessions just can send a 2,000 byte UDP datagram, but cannot send a 1,500 byte UDP datagram. This is largely due to, we'll get to it in a bit, PPP over Ethernet, which is still distressingly common.
What you said doesn't exactly match what's on the slide. Did you mean that 3% of sessions can send 2,000 byte fragments, or 3% of sessions which can send?
3% of the sessions which can send fragments can't send a sub-fragment value that would be fragmented on anything other than an Ethernet network. So I hope that's precise enough. Basically, they don't have a full 1,500 byte Ethernet MTU, and something keeps fragments from working. Our server, Java does not allow us to send raw packets. Our servers do. So we have a UDP echo server that reads and writes raw UDP packets. It can return the size of the initial fragment received, so we can see what the fragment is. It can send packets with df set and specific size, replies with ICMP6 too big. It basically supports trace route functionality from the server to the client with path MTU discovery, so we can figure out where the path MTU bottleneck is. And the network's mostly, but not all, Ethernet. There's this great quote, I don't know what the physical layer 20 years from now will look like, but it will be called Ethernet and have a 1,500 byte MTU. Well, at least right now. But there's a lot of PPP over Ethernet still out there. There's a lot of old DSL modems, and they're configured with PPPoE.
What's the denominator for all this? How many sessions?
What do you mean? This is for all our user base of 300,000 plus sessions. So this is a good representative survey of the internet modulo. We would have hoped that with the number of geeks involved, this would be lower because geeks are willing to pay for better internet and upgrade their modems. So that's kind of distressing. In these cases, where you should get an ICMP too big sent, only 60% sent them. So path MTU discovery for IPv4 has been decreed broken on the internet. It doesn't work. 40% of the time, you never get the ICMP too big. And basically, path MTU discovery must use fallback when ICMP isn't received. Oh, and you guys don't have this problem, but we do. Linux uses PathMTU discovery on UDP by default, and it sets the DF bit on all UDP datagrams that aren't fragmented by the network driver. Don't ask me why.
Question. With 8% of sessions, this is joined from how many hosts?
About 250,000 hosts or so, over 200,000 plus.
So Nick, a high-level question. How did you decide to look into IP? Among all the network characteristics, what motivates you to looking at these two?
Basically, we've motivated by looking at problems that we've personally experienced. We've personally experienced a problem where in the middle of the network there was a PathMTU hole, and that broke SSH connections from Germany to ICSI, but not from Germany to Comcast to ICSI, because it was in the middle of the network. So that's how we chose that. So proxies are another thing that we see way too many of. They're delicate things. Proxies assume that the traffic conforms to the protocol. But we control both ends, because for everything but HTTP and DNS, we're connecting to a custom server on our end over a custom protocol. Namely, you connect and it sends back the IP and port number. So this allows us all this port filtering policy. If the response is received as expected, we don't detect filtering. There could be a smarter proxy that goes, oh, this is just somebody playing games, I'm going to allow it. If the IP address is changed, this says either this protocol is redirected through a different computer, or the user has a load balancing network connection between multiple IP addresses, or the user started Netalyzr, closed it, and opened it elsewhere, which is why these days we do tests in order, so we'll see that. If the connection fails, so if you get a connection and then no data back, then the port is blocked somewhere in the network if the connection fails altogether, so the SYN fails to connect. But the interesting thing is the connection succeeds and different data is returned, it passes through a declared proxy. The proxy actually sent something back that was unexpected to us. And if the connection succeeds but no data is returned, then the request or response was blocked by a network device that was probably protocol aware, that something in the network goes, oh, this is a protocol violation, stop it. And that's actually quite common. So a few surprises. POP proxies are amazingly common. 7% of sessions reject our protocol violation, and another 6% actually send us a proxy banner, and it's almost invariably localhost antivirus. That the localhost antivirus routine is block mailworms by intercepting POP connections. They don't actually end up intercepting IMAP SSL or any of those. So it's questionable how well it works in practice, but we see a lot of it. NATs do FTP proxies. For those who remember Networking 101, FTP is broken in backwards. So the data connection comes from the server to the client. So most NATs, or a large number of NATs, just don't bother doing port forwarding and parsing the protocol. They just run a proxy.
What? NAT? There's a network address translation?
Yeah, the home gateways.
Okay. Put the S, that's kind of...
Yeah. Sorry, I capitalized the S. Oops. SIP-aware devices are amazingly common.
So this local antivirus program sending something to the client, how do you know? Do you have screen capture?
We don't have screen capture. We have the banner that it returns. And often the banner says AVG POP proxy. So the data coming back is specifically saying what the product is. SIP-aware network devices are surprisingly common. This is a big headache for those doing VoIP work. We saw less SMTP filtering than we expected. Only about 25% blocked SMTP requests to our server, and 8% rejected the protocol violation, which basically suggests that many ISPs are doing port 25 filtering dynamically. They're looking at the network. If you have a little port 25, they allow it. If you have too much, then you're blocked. This is a compromise. This keeps the spam bots from spamming, but keeps the support calls down. Expected results. Port 443 is almost completely unmolested. Run an SSH server on port 443 back at your home institution. You will thank yourself when you're on oddball networks. And the Windows port blocking is very common. And this was distressing. UDP port 1434, the slammer worm of, 8 years ago? That single UDP port, which is in the ephemeral range, so you can have stuff randomly assigned to use that port, 20–30% of the net still blocks it. It's kind of distressingly high. DNS is commonly firewalled. 99% have DNS access. That is, they can seem to contact our server. But of those, 10% fail to fetch non-DNS over port 53, which says there is some device in the network path that's going, oh, this doesn't look like DNS, kill it. Which means you better hope that as you deploy DNSSEC that this device actually understands DNS enough to not kill your legitimate DNS traffic. DNS is somewhat proxied. 1.4% have the DNS request that is sent from the client direct to a remote machine redirected through some other system. In this case, I've seen NATs where if you don't set the recursive desired bit, it will actually even block those connections. DNS filtering on the wire, you see that 10% number? A lot of these devices we've already shown don't actually understand the DNS protocol. Quad A records get blocked. Text records get blocked. Unknown resource records get blocked. eDNS gets blocked. Oh, you wanted to use DNSSEC to validate certificates so you don't have to deal with DigiNotar Part 2? Sorry, you are out of luck. The network has decreed DNSSEC shall not work for 1–2% of users. This is actually a big problem for those who want to do DNSSEC to reduce a lot of the certificate problems. HTTP proxies. Well, we took advantage of a custom HTTP server. So known headers, random capitalization. Any proxy that resynthesizes headers will change capitalization. So if you see the capitalization of the connection header changed, that may be a censorware proxy. At least one vendor changes just that header's capitalization. HTTP proxies might not handle unknown requests. They may have a bug that's now 2–3 years old at this field where it follows the host field. About 5% plus show evidence of some HTTP proxying, so it's significant. We also detect caches because a hidden cache must cache. So basically, by having a custom web server, we can lie about the cache control headers. And so the first time you fetch an image, it shows up like this. The second time you fetch the image, it shows up like this. Same size, different MD5. Known size. 4% of IPs show in-path HTTP caching, which be all fine and good, but 50% of the caches are broken. 50% of the caches cache data that the server says, oh, cache, any cache that may exist in the network, don't cache this, please. They cache it anyway. Hidden filtering must filter. About 10% of hosts have virus filters that are running on the end host itself. We test with the ICAR test virus.
What instruction are you using for don't cache? Are you using all of them? Or
we do weekly of kindly, sir, don't cache, and strongly, which is everything that says don't cache this thing.
So 50% is even with the strong one?
A lot of this is with weak. A lot of this with weakly uncacheable will still cache. But we do see a fair number where strongly uncacheable will still cache. Like during development, we had problems where the NSF network would change connection from close to keep alive, and we weren't handling that. And it would cache things that were explicitly marked as, oh my God, do not cache.
So are these the ISPs
These are usually ISPs in foreign countries where bandwidth costs more, or corporate networks.
Yeah, it's a similar question. So basically, we have 4% of IPs, then it's about like more than 10,000 IPs, right? So did you try to look into the cities and then particular areas?
We haven't looked into geographical beyond just sort of country level. That certain countries are much more prevalent than others. So like New Zealand, you see a lot of web caches.
So what would be a hunch? Like it will be a few ISPs, or it will be?
It's very, very rare among US ISPs. It is much more common among foreign ISPs where they have high transit costs.
Undesired caching. But if the client sends whatever they reload, or if modified sends, I would assume that they honor that and then batch it forward.
We don't check for that, but I would not bet on it, since they were caching stuff that were marked from the server as, oh my god, do not cache, so that the browser itself should always be generating new requests. Another problem we see is big buffers. They're all over the place. They're in access devices, they're in network drivers, they're in wireless access cards. Basically, everywhere there's a buffer, there's odds are somebody involved in building it thought bigger was better. And so what we do is we just do a UDP hammer. We do a max rate UDP flow, see how much the latency increases, then go the other way and see what happens the other way. And it's just an endemic problem. So this is what we call the graph of pain. Basically, it's the upload bandwidth and the inferred buffer capacity based on the delay and packet size. And we get nice vertical striations suggesting that we're getting realistic measurements of buffers. We get nice horizontal striations that indicate common service tiers. Anything right of the green line, under stress, the user experiences a half second of latency. Anything right of this red line, under stress, you can induce 2 seconds of latency into the user's connection.
Can you elaborate a little bit why big buffers are bad?
OK. I'm a full rate TCP flow. I fill up the full buffer, and I'll alternate between full and half fill and the sawtoothing. If the buffer is a simple drop tail queue and I have some latency sensitive thing like a SYN, that SYN now sees that full buffer delay as the packet goes through. And basically, the net can't walk and chew gum.
Are most of the buffers drop tail?
Yes, because a lot of these are either in the wireless card or in the access device, the cable modem and DSL modem hardware. This is downlink is fairly bad, uplink is worse. And it basically is, until you do a full rate transfer at the bottleneck, there's no problem. Once you do, everything interactive goes to heck. This is why if you have roommates, don't allow them to run BitTorrent. Your gaming will suffer. Even if we just do users self-reporting as wired connections to exclude the wireless buffers, which are unfortunately big, we still see a lot of systems with very large buffers. So we're able to fill up buffers, and if we can fill them up, a TCP flow can. And if it's just a drop tail queue, they're in trouble. We have this lovely graph of just Comcast users. God bless biases in your data set. Well, we only really see 2 big bands of capacity, which is what you'd expect. They're more homogeneous. They have a lot of rental cable modems. And there's at least some suggestion that some cable modems actually implemented buffering properly. That is, in a simple drop tail queue, you put a max delay, not a max capacity. And you do that, and you get good behavior. It's great if you're doing just dumb drop tail queues. It gets you 90% there with just a comparator and a timestamp. However, we tracked down these cable modems. It looked like one old Linksys. I bought one of these off of Fleabay, plugged it in, and got the Comcast walled garden saying, this cable modem is too old to connect to our network, which suggests that at least one hardware vendor used to get it right and then doesn't anymore. But basically, it's the walk and chew gum problem. There's some work for 90% solutions, smarter NATs. I hate NATs, but if you're going to have them anyway, you can have them do queue management so that you can fix your network with a better NAT. The 100% solution is very hard. Basically, every buffer which might be congested needs smart queue management. And this is required if you want sub 100 millisecond latency under load. So if you want clean VoIP when you're doing full bit torrents, you need smart queues. NX domain wildcarding is endemic at this point. This is the problem where you do a typo and you get to a helpful search page from your ISP. Strangely enough, this helpful search page is filled with ads. When they do wildcard, they're often broken. Seriously, they don't just wildcard www, which the browser generates. They'll wildcard anything. So they basically assume that every DNS lookup is only from a web browser, because the only thing they return is the address of a web server. 6%, most of these being OpenDNS, but some non-OpenDNS. Wildcard serve fail. They don't care to limit collateral damage. 1% of the non-open DNS sessions, 5% overall, will wildcard an A record for a zero answer reply. So if I have an IPv6 test site, it returns a quad A record, and queries for the A record return a valid answer with a zero number of answers. So it's basically the server is saying, this name is valid, there's just no record for it. OpenDNS wildcards up a record. You cannot build an IPv6 test site and expect it to work reliably if you have open DNS clients. This is a bug. I reported it to them months ago. As far as I know, this bug is still there. If you're going to use third-party DNS, use Google Public DNS. It doesn't have these issues. And this is disturbing. We actually tracked down the vendor literature. This is for $1 to $3 per customer per year. That for even a big ISP is slightly more than pocket lint, they will drastically change how the internet operates. But this is the interesting one, and this directly affects this company. Some ISPs were manipulating DNS results for Google, Yahoo, and Bing. This is what I showed at the start. Yahoo and Bing lookups always return the IP address of a third-party controlled proxy in one of two address ranges. Google was sometimes faithful, sometimes an ISP-controlled proxy, sometimes a third-party proxy, and the behavior was set per ISP. So the ISPs had specific control over how Google was manipulated. Google put a halt to all Google proxying back in May by throwing up a CAPTCHA on the search page with a link to a page of, why did I get this CAPTCHA? Your ISP is doing this stuff without your permission. Presumably, they also called their lawyers involved. Depending on most lawyers you talk to, call this wiretapping. And the records are for a clear proxy. This isn't Akamai notes. So when Yahoo and Bing don't have clean reverse, we now do a direct probe of the server, because a lot of them, Akamai, you don't get clean reverse DNS on. But these are not Akamai notes. These are proxies. Proxy traffic appears to be unmolested. As we will see in a sec, it's not the case. HTTPS proxy is proxy to Google unmolested, because Google is the only one that runs HTTPS services on any of these domains. So if you are set to one of these rogue DNS resolvers and go to https://www.bing.com, you get a complaint from your web browser going, this certificate's only for Google. The non-proxied hosts return a redirect to 255.255.255.255 so that we can see that it's proxying all three of these, and the banner reveals that it's squid proxy. Invalid request put up a page referring to phishing-warning-site.com, which is a GoDaddy parked domain with anonymous registration, and would be a dead end, except that if you Google for phishing-warning-site.com, you get complaints about Google being down. Because if the proxy has an internal error, it also throws up this banner. So when the proxy breaks, the user thinks Google is down, sees this banner, and if you search for it, you get this. So anybody who has friends on the DNS library side at Microsoft, client-side DNSSEC validation is a must-have. We cannot trust the recursive resolver. So why were they doing this? Well, these ISPs had this behavior as of this summer. Cavalier, Cogent, DirectPC, Frontier, Fuse, IBBS, Insight Broadband, Megapeth, Paytech, RCN, Wide Open West, and EXO. Who here uses Frontier? Double check your network or use a third-party DNS resolver.
How do you conclude these ISPs have this?
Because when we do these lookups on the client, ship them to the server and record them, and we saw that these ISPs were routing the user requests for Yahoo and Bing through these proxies.
So you have sufficient clients from particular ISPs?
Yes. Dozens to hundreds, depending on the ISP.
And they all experience problem?
Almost all of them. It depends on the ISP. So like Paytech, only one of their resolver clusters used this, and other ones did not. Frontier, pretty much all their resolver clusters did this. Actually, Weidong, I'd like to talk to you later. We'd like to do some testing with Frontier.
My network?
Yeah.
Frontier on my network.
Your home network using Frontier.
I'm kidding.
So Charter was doing this, but they stopped. And Iowa Telecom was doing this, but when they got bought by Windstream, they stopped. Who was responsible? This lovely company called Paxfire, who specializes in monetizing DNS. We found Paxfire's demonstration servers and a bunch of other evidence. We also found collaborating data online. And this was the one that stumped us until just a little over a month ago, is why we couldn't get the proxies to change. Note that also there's a MSR paper that also noticed this, but as far as I can tell, didn't answer the why question either, let alone get the publicity. It turns out there was the Google post had a pointer to another blog post that had a URL that was changed, and that allowed us to determine the condition. If the query was from the browser search or URL bar only, and the query matched one of at least 165 specific keywords, then replace search results with a 302 redirect through an affiliate network.
How do you know whether the query was from the browser search or URL bar?
I will get to that. Because this is what happened. Let's say the search is for CA. They're interested in the state of California. Standard flow goes to the resolver, the DNS appliance lies, and goes to the proxy. Now, the proxy actually observes two things here. The first thing it observes is that it's for a keyword search. And the second is the URL actually does say this is from the browser URL or search bar, not from the Bing homepage. So it looks for both of these conditions, does a 302 redirect, in this case to Paxfire's own analysis server that goes, oh, this is for a specific affiliate program, which goes and does a 302 redirect through the affiliate program, which then goes and does a 302 redirect back to the final merchant, and after the final merchant gets the request, well, in this case, the user ended up at the Computer Associates web store. In the process, presumably the merchant pays the affiliate program, which pays Paxfire, which splits the money with the ISP. Sounds like very complicated, but let's see basically real time. Well, it bounces back and forth, and the page renders. And how are users supposed to know about this?
How did you hit these queries?
What we did is we took the Alexa top 10,000. We stripped out the suffix, so it was just the domain name, so like Google, Yahoo, Amazon, EC2. And we bombarded this server with queries to see which ones it would modify.
Okay, I have this
I
question.
assume they sued you for modifying their network traffic.
No, they've sued us for libel because we pointed out that they've sued another party for libel because we pointed out that this can monitor user search. They don't claim to monitor user search, just modify it, so it's okay.
How long does it take to run analysis from end to end? I have a question.
Netalyzr takes about 3-4 minutes.
3-4 minutes.
We do a lot of tests. So they do modify and monitor, but they claim not to record and profile. So from their point of view, it's okay.
Well, the user clearly notices.
How?
Well, because you didn't get the query results, but rather.
How many users would actually notice this? Wei Dong, do you use Paxfire or do you use Frontier's DNS resolver?
Actually, G2 just emailed you and me. I assume he's watching somewhere.
Yeah.
And I never observe anything bad. I search Bing. I always get Bing. Basically, I think Frontier.
Do you use
search bar? Yes, I do.
Well, do you hit the keywords?
No, like IE now doesn't have search bar. It's all in the address bar. You get I don't know.
Interesting stuff.
Yeah. But let me finish. Let me finish what I want to say. It's basically, I know Frontier is doing one weird thing. If I type an address, it's wrong. It's not resolved correctly.
Yeah, that's
it will
different.
redirect that to their own search engine.
Yeah, that's their NX domain
you're trying
page.
to search this website.
Oh, actually, talk to us. That opt-out is if Frontier does not add a new opt-out, the opt-out they provide on the bottom of the page is fictional. It just sets a browser cookie, so the next time you go to the page, it sends up a fake browser error message. I have a protocol for testing their opt-outs, so let's communicate afterwards. So on the 26th, we measured the monetization web of the things they'd manipulate. Some were redirected direct to Amazon. If you did Amazon, eBay, PayPal, it went direct because they have direct affiliate programs. I got to see, before I got tired of copying company logos, Alibris, Computer Associates, CompUSA, Dino Direct. They went to through Linkshare. Google Affiliate Network went through a lot. 2 of which are of note. If you typed in HBO or FIFA into your address bar on the 26th, you would get to a page saying this double-click URL is wrong. So you wouldn't even get to the final destination. Some went through Ask. All of these ended up going to yp.com. With a banner in the top. Did you really mean the site you were looking for or yp.com and a random yellowpages.com listing in it? Kohl's was especially amusing on the 26th. You would get a Kohl's web page framed with an ad for JCPenney. A lot went through Commission Junction. They're the biggest. I gave up at A. And some Commission Junction was then redirected to DoubleClick for these airlines. During this process, it's unclear whether anybody understood how Paxfire was driving the traffic. So
are these people actually paying Paxfire?
Presumably, because that's how it works.
So to them it looks like that someone went to a search site and clicked on a link or something?
Yeah, or an affiliate ad. So an ad on somebody's web page. So
Google use Paxfire.
All 3 big affiliate programs, Linkshare, Google, and Commission Junction, suspended the accounts within 2 business days.
So they
They didn't know, as far as we know. So the current situation, they halted the proxy server redirection to affiliate links within 24 hours of public disclosure. But they've, as of the 16th, maintained the DNS redirections that are routing user traffic through the proxy servers. So they can resume modifying results at a later date, presumably. Why they haven't stopped, I don't know. Commission Junction, Linkshare, and Google have all publicly suspended Paxfire's account pending further investigation. We haven't heard anything more from them, but they've all publicly stated the account is at least temporarily suspended. And so that's amazing what ISPs will do to manipulate traffic. Like, we now see at least 2 ISPs that do in-path 404 rewriting, where they have an IDS box that looks at HTTP replies, and if the HTTP reply is a 404, they inject a JavaScript redirect to their advertisement page.
So Paxfire actually, in this
But
case,
that's a different company that's doing that.
so it felt like the ISPs are the problems.
Both.
Both.
There are ISPs that use Paxfire for NX domain wildcarding that don't do this behavior. It's both.
It felt like Paxfire is just exposing a service. I can provide you additional patterns.
That's what they sell to the ISP, but they're direct participants in the traffic. They're the ones running the proxy servers. So they are the ones that are providing the infrastructure and running the systems that are monitoring user search requests and modifying the results, or at least were monitoring and modifying. So conclusions, well, this worked. We actually did write once one run anywhere and actually got it to work. You can, as a small group, build a robust and comprehensive network measurement and diagnostic tool. We got slashdotted and sysadmin never noticed, with a tool that does full rate UDP flows for 10-second bursts. We didn't get noticed. We did a lot of sneakiness because, well, the network is your adversary these days. Oops. So we viewed the network as an adversary and tried to trip it up. And we found interesting things. Thank you.
So how do you turn this into sort of a longer-term monitoring strategy? Because it seems like things like Slashdot, you're only going to show up on Slashdot once or twice.
A lot of users use it for debugging now. So it's become something that people run on a regular basis. We're 20 to 70 sessions an hour just at random baseline at this point because of random links, people running it, people getting to Starbucks and running it, et cetera, et cetera.
Are the administrators running these?
A fair number of network administrators really like the tool because it allows them to help debug their own and their parents' networks.
But when you say debugging performance, connection, or
connection problems like NAT issues.
but if my connection doesn't work, I may not connect to your server. How can you help me diagnose?
Because there are a lot of problems where the connection sort of works. So, for example, the internet seems slow. What causes the
problem?
Yeah. Or some sites aren't loading right. That could be a DNS error. So, like, for example, OpenDNS by wildcarding serve fail. If the site's DNS server is down, you'll get oddball OpenDNS stuff rather than the legitimate response. So there's a lot of things like that. There's a lot of just weird edge cases. One of the tests we do is background outages. So the test takes 3 minutes. During that 3 minutes, we do one ping every 1/10 of a second. If we lose 3 packets in a row, we alert that. So that says your network is flaky and dropping.
So Nick, you also did the tripwire work with Charlie Rice before. Can you put them together somehow? I mean, that way?
We actually do use the tripwire test to see if we're in a frame, and we do direct HTTP requests to see if some replies are modified. So we do similar detection. So we include tripwire functionality in this. Oops.
So do you So in that work, you discover a bunch of ISPs injecting content into the result page.
Yeah, and we see 2 ISPs injecting content into 404 pages, which is something that you'd actually really not be able to do with a tripwire, because it's really kind of because of how the framing and stuff like that works and the redirections. So there's a lot of that stuff.
So for IPv6, it seems like there's a lot of negative lessons here. There's a lot of things that will break. Is there anything we can take as a positive, like here's a way in which we could deploy IPv6?
IPv6 is actually looking remarkably good in our data. About 5% of the users have IPv6 connectivity. The gross problem of broken IPv6 means broken internet to dual stack sites is no longer the case. That Apple and Opera fixed those showstoppers. So now they're basically, everybody's doing happy eyeballs. So that if you get a quad A record and an A record, you try them both. If whichever one finishes first is the one you use. IPv6 path MTU discovery is much less broken than v4, mostly because most IPv6 is going through tunnels. But at the same time, it has that minimum 1280 byte MTU that's enforced in the spec. So the path MTU and fragment issues for v6 seem to be a lot better. One of the things that's nice for v6 is it gets the NATs out of the way, because the NATs just pass traffic. So it reduces the fragment problems. Port filtering on v6 is vastly less than v4. A lot of computers have v6 without knowing it because of Teredo and 6-to-4. The situation with 6-to-4 is now vastly better than it was a year ago, where 6-to-4 turned on would mean your computer broke for dual stack sites. Now it just means if 6-to-4 is turned on and it doesn't work, and it doesn't matter.
6-to-4, and are those deployed on the server side?
Those are deployed in the network infrastructure. So how 6-to-4 works is your v4 packet, or your v6 packet, you encapsulate it in v4 to a special Anycast address. It gets to the first one, strips it out, sends the v6 on, and then the v6 has your v4 address embedded in it, but goes to a special v6 Anycast address, gets to a proxy that re-encapsulates it and sends it on.
Are all the networks, are all the major ISPs?
Very few ISPs are. 6-to-4 is actually something that's just on the client. Teredo is just on the client, and Microsoft has it on Windows, and it actually works most of the time now. So the v6 story is, it's still pretty rare, on the order of 5%, but it's not breaking things, which means turning on v6 is no longer the catastrophe it was a year ago. And some retail ISPs are shifting to it. So like Comcast is supporting v6 in trial deployments as native v6 to clients. I think mostly because they want to use dual stack Lite to handle the v4 address space exhaustion problem.
Great. So we have a half-an-hour break. I'm sorry, are there any more questions? So we have a half-an-hour break, and then the next talk starts at 11:30.
Cool.
Yeah.